Welcome to the Better Battery Safety and User Experience. Thank you for joining us around the world. Our speaker today is Gaupe Damli. He's a business director at Maxim Integrated. He's responsible for the battery management and product line. His current interests include battery and power management, such as fuel gauges, battery safety, protection, and authentication, wireless power, and USB Type-C power delivery battery charges. He's joined Maxim in 2005, and he's based in Dallas, Texas. Welcome, Gaupe. Please take it away.
Thank you, Felipe. Today, we will discuss how Maxim can help system designers improve battery safety and user experience. The key market trends that are driving the need for better battery safety and user experience are faster charging, heightened awareness about improving battery safety, increased desire to prevent use of clone batteries, increased need to maximize runtime, and finally, increased desire to see reliable information about the battery. A battery fuel gauge or gas gauge is an integrated circuit that determines battery state of charge, also called SOC, and state of health. A fuel gauge IC can predict how much longer the battery can continue to provide power under specific load and temperature conditions. Inadequate battery life and unreliable battery SOC reporting are some of the most common complaints about any battery powered device. A fuel gauge that overestimates the SOC can result in surprise shutdowns, while a fuel gauge that underestimates the SOC will cause the system to shut down prematurely, even when there is energy left in the battery. Either situation can be avoided with an accurate battery fuel gauge. Hence, it is critical for good user experience. Fuel gauges can be implemented in two ways, host side or pack side. The system block diagram at the top shows a simple battery pack on the left side connected to the host system on the right side. The host system contains the application processor that communicates with the fuel gauge IC mounted on the host side. This architecture is suitable for a system with an embedded battery or even a removable battery if the system is expected to be used only for a few years, or also in very cost-sensitive applications. The system block diagram at the bottom shows the battery pack on the left side that contains the fuel gauge IC. The host system communicates with the IC to get fuel gauge information, protector status, and charging prescription. This pack-side fuel gauge contains the battery model and other important information such as learned parameters and life logging. The advanced integrated protector monitors fault conditions beyond voltage and current, such as temperature, and others that we will explore further today. This architecture is suitable for long-life systems with a removable battery. This approach is also suitable for secure authentication to help prevent clones. Because of the non-volatile memory requirements inside the fuel gauge IC, this approach is slightly more expensive than the host side approach. So at this point, let's take a quick poll and understand, do you mostly design with fuel gauges on the host side or pack side or both? You can check both answers if that's the case in your designs. Let's take a few seconds for the responses to come in. Okay, thank you very much. We will move on from this poll question. Now let's take a look at the common design challenges and the solutions that Maxim has to offer. Every lithium-ion battery needs a protector to prevent damage and hazardous outcomes when subjected to abnormal voltages, currents, and temperatures. Maxim offers fuel gauges with integrated two-level protectors that activate when the primary protector has failed or when the battery has seen such an abnormal voltage or temperature that it should not be operated anymore for safety reasons. As some batteries age, they can develop tiny internal shorts. In some rare cases, these shorts can grow and result in thermal runaway conditions. Maxim fuel gauges can detect such internal self-discharge and help identify and cut off potentially hazardous batteries. Use of unauthorized, poorly designed clone battery packs may have hazardous outcomes, especially if the charger uses a higher voltage than what the clone battery is capable of handling. Secure authentication can prevent such clones. After a new purchase, system designers want to delight their end users by not requiring them to charge before first use. This requires that the battery shelf life to be very long. Maxim ICs operate at 85% lower quiescent current than the competition. Typical fuel gauges require the battery to be characterized for best performance. This can take several weeks. In fast time-to-market situations, designers can now use a simpler process that eliminates such characterization in Maxim fuel gauges. Mobile devices need an accurate battery status indicator to prevent premature or abrupt shutdown. Maxim ICs provide 40% better accuracy than the competition. In case of multiple series cells, some cells can become mismatched as they age, because of which the cell that reaches empty first determines the runtime. By balancing the cells, the system is able to squeeze out more runtime. Here's a typical implementation of a one-cell battery fuel gauge on the system side. A Maxim fuel gauge IC measures the voltage of the battery current using a high-side sense resistor that is accumulated to give a Coulomb count, and temperature using an on-chip sensor or an external thermistor in case the battery is located far away from the IC. The fuel gauge provides state of charge, absolute capacity in milliamp hours, time to empty, and time to full while charging, and this information is critical for improving user experience. Here's a multi-cell battery fuel gauge mounted on the system side. The IC measures the voltage of the battery through a high impedance resistor divider, and so it can support any number of series cells. The IC also measures current using a low-side sense resistor and temperature using an on-chip sensor or an external thermistor. The fuel gauge provides state of charge, absolute capacity, time to empty, and time to full, again improving the user experience. Here's a one-cell battery pack with the fuel gauge mounted inside. The IC measures the voltage of the cell, current using the sense resistor, and temperature using an on-chip sensor or external thermistor in case the cell is located far away from the IC. The protector control drives a pair of high-side N-channel FETs. The IC also triggers a secondary protector for harsh faults that necessitate the battery to be permanently disabled for safety reasons. This is a 2 to 4 series cell battery pack with the fuel gauge inside. The IC measures the voltage of each individual cell and balances the charge using internal FETs and balancing resistors. It also measures current using a sense resistor and temperature using an on-chip sensor and up to 4 external thermistors, since the cells are likely to be located far away from the IC. The protector control drives a pair of high-side N-channel FETs. The IC also triggers the secondary protector for harsh faults. To power small loads like real-time clocks or housekeeping microcontrollers that need to be always on, the IC provides a regulated output that stays alive even when the primary protector kicks in. This output powers down only when the cells are severely depleted and therefore need to prevent any further drain for safety reasons. Here's a multi-cell battery fuel gauge on the pack side. The Maxim IC measures the voltage of the battery through a high impedance resistor divider so it can support any number of series cells. The IC also measures current and temperature using an on-chip sensor or an external thermistor. So let's take a quick poll and see how many series cell does your lithium-ion battery have. You can choose multiple answers from here. Is it just 1 series, 2 to 4 series, or 5 series or higher? Again, let's take a few seconds to answer this. You can select more than one answer in case you design systems of multiple kinds. Thank you very much for all your feedback. Let's move on. Lithium-ion or polymer batteries are very common in a wide variety of portable electronic devices because they have very high energy density, minimal memory effect, and low self-discharge. However, care must be taken to avoid overheating or overcharging these batteries to prevent damage, potentially resulting in dangerous outcomes. By operating in safe temperature ranges, at safe voltages, and under safe current levels, overall safety can be assured throughout the life of the battery. All these protection parameters can be easily set up using the configuration wizard in the evaluation kit GUI as shown here right now. Simple protection schemes are available to protect the battery from exceeding safe levels. These include protection for over-discharge current, short circuit current, overcharge current, under voltage, and over voltage. The next level of protection offers smart protection schemes, which include protection for long over-discharge current, over-temperature limits for charge and discharge, under-temperature charge limits, charger communication timeout, overcharge capacity fault, and excessive imbalance between multiple series cells. The IC also provides a novel deep discharge state protection that is immune from load and resistance variation. This leverages the fuel gauge that provides the equivalent open circuit voltage even under load. This state-based protection prevents nuisance trips that would otherwise happen with a conventional under-voltage protection under pulse loads, and hence extend the battery runtime. The Maxim IC provides all of these simple and smart protection schemes with programmable thresholds and programmable timer delays for each fault. The ICs also provide programmable charging current and voltage prescription considering the JETA temperature regions as well as step charging. As some batteries age, they can develop tiny internal shorts due to harsh operating conditions exacerbated by latent manufacturing defects. In some rare cases, these shorts can grow and result in thermal runaway conditions. Maxim fuel gauge ICs can detect such internal self-discharge and can help identify potentially hazardous batteries. The IC can alert the system or shut off the battery at programmable internal self-discharge levels. On the right, the test result in teal shows the measured leakage of a normal battery at close to 0 milliamps, just like expected. When a 900 ohm leak is added to simulate a leak in a potentially hazardous battery, the test result in orange shows that the Maxim IC now measures about 4 milliamps of internal leakage. The algorithm for measuring internal self-discharge is not affected by variations in operating temperature. This is very important in preventing false alarms. With increased market success of the device, the attraction to clone the battery pack by unauthorized third parties also increases. A clone battery pack not only causes loss of revenue, but also increases the risk of a poorly designed battery pack causing safety and liability issues. Maxim ICs integrate secure SHA-256 authentication using a 160-bit secret key. The security design draws on more than 20 years of experience that Maxim has in various areas, including cryptography, IC-level physical protection, as well as a security-oriented manufacturing flow. The ICs offer highly customizable options that can be chosen based on how secure the host is. In case of a secure host, in which the reference secret key can be stored safely, the IC provides an implementation option that allows a unique key in every battery pack. In addition, this option also allows the key to be generated using a multi-step approach that keeps the resulting key safe as long as any one step remains uncompromised from an attack. In case of an unsecure host in which the reference secret key cannot be stored safely, the IC provides an implementation option to allow creating unique intermediate keys on the fly in the battery pack. For any mobile device using a lithium-ion battery, knowing the correct state of charge is critical for good user experience. Maxim fuel gauges provide excellent accuracy over various load conditions shown here with effective runtimes of 3 to 32 hours and temperatures of 0 to 40 degrees centigrade. Under these conditions, the state of charge error is less than 1%. The ICs also work very well for even more extreme conditions like very short runtimes, for example, just 10 minutes, as well as very cold temperatures like minus 30 degrees centigrade operation. The fuel gauges also provide dynamic information about the peak or sustained load or power limit that the system can use to throttle and keep the load below these limits and prevent a battery crash while operating at peak performance. One of the big challenges for fuel gauges is that traditionally they have required extensive characterization and analysis of each battery for specific application conditions for getting the base state of charge accuracy. This means that the system designer has to perform complicated characterization on their own or ship the battery to the fuel gauge vendor. With new transport safety regulations, this has become a complicated logistics effort. Once the battery arrives, the fuel gauge vendor can take 2 to 3 weeks for running the tests and analyzing the results. This time and effort make it difficult to support fast-track projects or projects with uncertain volumes. Maxim fuel gauges provide a solution by supporting ModelGauge M5 Easy that eliminates battery characterization. The system designer can use the evaluation kit software to step through a few application details and generate the model in just a few minutes. Maxim has run simulations using more than 300 different batteries and 3,000 discharges and summarized the results in the form of a histogram that shows that this easy method results in less than 3% error in more than 97% of the test cases. Maxim fuel gauges offer the lowest quiescent current in the industry. This helps prevent the battery from draining during extended periods of standby or even when the devices are simply stored on the shelf. This table is provided as a reference. Please refer to this detailed comparison chart to understand the key differences in the various options you have for one cell implementation. This second table is also provided as a reference. This shows the various multi-cell fuel gauge options for 2 series, 2 to 4 series, as well as for more than 4 series. In summary, Maxim fuel gauges integrate highly programmable protectors for lithium-ion batteries to prevent damage due to abnormal voltage, current, temperature conditions, and to ensure safe charging and discharging in a wide range of applications. The ICs reduce the overall solution size and make small form factors of batteries viable. Internal self-discharge detection helps avoid problems due to unsafe cells. SHA-256 authentication provides robust security to prevent clone battery packs. ModelGauge M5 algorithm provides industry-leading accuracy that can be used to maximize the runtime and improve user experience. ModelGauge M5 Easy configuration eliminates battery characterization for most common types of cells and makes it very easy to design the fuel gauge in your applications. And finally, very low quiescent current helps prevent the battery from draining during extended periods of standby and enables long shelf life and runtime. Thank you for joining us. Back to you, Felipe.
Thanks, Bakul, for a great presentation. And before we start the Q&A, I want to draw attention to the Contact Us window on your screen. If you'd like to get more information about the products we have talked about today, please fill out the form and we'll contact you and follow up with you. Also remember to check out the resource list to access all the documents, the slide decks, and links that we have provided for battery management information. All right, so there's a lot of questions that came into the chat, Bakul, and we have lots of great questions, so we're gonna try to address them as soon as possible. So let's start it right away. So here's the first one. Are there any limits on battery capacity for your fuel gauge products?
So Maxim fuel gauges can be used for very tiny batteries that have just 20 to 30 milliamp hours, as well as for thousands of milliamp hours, or actually tens of thousands of milliamp hours used in energy storage devices. So our devices do not have any limitations about the capacity as such. There are very few constraints, and those can be adjusted by selecting the right sense resistor. There is one IC called MAX17263, which has an integrated on-chip sense resistor. So for that, of course, there are certain capacity limitations that you can find in the data sheet.
All right, great. Thanks again for that answer. And let's move on with the next question. What type of design is required to have a secondary protection?
So the need for secondary protection can be dictated by two things. One is what safety levels is the design trying to achieve, and the second is the application specific. So a lot of times in medical devices, or when there is a critical need to ensure safety, there are secondary protectors used in addition to the primary ones. So what happens is that our ICs provide the primary or the first level of protection, and they can actually assist a completely redundant secondary protector, because most of these secondary protectors are very simple devices. They just measure voltage and current, while our devices also measure temperature, and they can keep track of severe over voltage or severe over temperature conditions that make it necessary to cut off the battery completely from any further use.
All right, let's go to the next question that I have here. Can host side fuel gauges be used as pack side?
So that's an interesting question, and the answer really depends on the way the battery is being used. In case of an embedded system where the battery is never replaced by the end user, it really is an artificial line in terms of what you call as pack side implementation or host side implementation. So in that case, certainly you can use a host side fuel gauge, which essentially has no non-volatile memory. And at power up, the system application processor can load the battery model in it and run the fuel gauge correctly. The difference between the pack side is that in a pack side IC, there is non-volatile memory inside the chip itself that allows the end user to swap the batteries between different systems and so on, because all the information about the fuel gauge and learned parameters is carried within the IC itself.
All right, sounds good. Hopefully that addresses the question. And now we have one more question here that came in is, does your fuel gauge support lithium ferrophosphate or the lithium FePO4 battery chemistry?
Yes, so we are seeing a lot of interest in the lithium ferrous phosphate chemistry because they are certainly low impedance, they are safer, and so a lot of the high energy or the high pulse load applications are choosing to use this chemistry. Now, for fuel gauges, actually, it's a little tricky chemistry to work with, because if you look at the voltage curve from charging and discharging, and you look at the open circuit voltage, it actually has a little bit of a hysteresis. that can confuse some of the fuel gauges in the market. But our ModelGauge M5 fuel gauges have special algorithms already embedded inside that take care of these little quirks in this particular battery chemistry. And so our ModelGauge M5 fuel gauges can certainly work with the lithium ferrous phosphate chemistry batteries.
Great. Thanks again for the answer. This is actually another question that I myself asked during the presentation. How does the fuel gauge detect leakage?
So some of our new fuel gauges, they have the ability to detect the internal self-discharge that's going on inside the cell. This actually is a very tricky measurement because the sense resistor is not able to see that internal leakage. So what we do is we look at the coulombs going inside the battery or the cell, and we also monitor the coulombs that we take out of the battery when the load is going on. And we find out the difference in a very, very sensitive way. And that's, of course, happening over time. So the difference between the charge going in and going out divided by the amount of time in between, that essentially is used to calculate the internal self-discharge of the cell.
Great. That's awesome. I think that's good information. I have another question. I think you answered this one already, but make sure I just want to ask it in any case. Do you offer a fuel gauge that does not require sense resistor?
Yes, certainly. So we actually have two broad categories of fuel gauges. One we call the ModelGauge M5, which is a hybrid of coulomb counting and voltage measurement. And one of the fuel gauges called Max 17262, it has an integrated on-chip sense resistor. So if a system designer is just concerned about not requiring an external resistor for space reasons, that's one choice. In addition, we also have a line of products that uses an algorithm called ModelGauge, which is just voltage based. So there is no sense resistor used in this type of chip at all. And this is available for both 1 series as well as 2 series. They are called Max 17048 and Max 17049.
Great, thanks. There's another question here in the chat. With your fuel gauges, is this required to fully, sorry, I'm gonna read it again. With your fuel gauges, is it required to reach full or empty to learn the parameters correctly?
So again, that's an interesting question because some of the devices that you buy in the market, they first ask you to plug in the charger and make sure it's charged to full. And they may also ask you to completely run the battery down to learn correctly. Our fuel gauges do not require any of that sort of cycling for the battery. Our fuel gauges do not need to reach full or empty, or even standby for that matter. And this is actually very important because a lot of the applications today use some sort of a wireless connection, which may be dormant for a few minutes, but then every 10 minutes or so, there may be a pulse that disturbs the battery. And we have heard that it can basically mess up some of the learning algorithms that is available in the market outside. But the ModelGauge M5 and ModelGauge algorithms do not have any such problems with these sorts of pulse loads.
Great, thanks again. Let's go to the next one. What type of design suggestions do you have for secondary protection implementations? So when you use 2 levels of protection, which is first is our primary protection that our ICs offer, and pair it with a separate secondary protector, you do have to take care in terms of the thresholds that you use. Our ICs have a programmable settings, and you should target them
to trip the battery for any of the safety conditions that you have to take care of for the particular cell. And you should choose the secondary protector so that the thresholds are higher, so that you don't want the secondary protector to trip before the primary protector has tripped. You want the secondary protector to trip only in case the primary protector has failed, so that there is no interference between the two protectors operation.
That makes sense. Yep. All right. So there is another one that I think is pretty short answer. What fuel gauges can be used for both high side or low side RSense applications?
So I think the viewer is probably looking at a one-cell fuel gauge. In some of the projects, they may need a high-side sense resistor, while in some others, they may need to use a low-side. So we have a fuel gauge that is Max 17260, where the designer has the flexibility to implement a low-side or a high-side sense resistor based on their particular application requirements. In some applications, designers do not want to interrupt the ground signal, and so the low-side sense resistor option is not desirable in that case. So that's where you would use the high-side implementation with this Max 17260 IC.
Great, thanks so much. Okay. I think we're about to run out of time, and I don't have any more time for the questions in the chat. So thanks again, Bakul, for all the time, for the presentation and answering the questions from the audience. This is all the time we have today. Thanks for your participation. After the webcast ends, remember there's a book a meeting, and it will appear. Thank you for joining us, and have a good day.
Thank you.